We'll start in 1 minute. We may start section 11.8 on power series later today, but first we'll finish section 7. So we'll see if we can determine if a number of infinite series converge or diverge. So for this one, the terms of the series are 3 to the n times n to the second divided by n factorial, and n ranges from 1 to infinity. So on this one, let's try the ratio test. Okay, so the limit as n approaches infinity. And then in absolute values, we have the n plus first term divided by the nth term. So we have 3 to the n plus 1 times n plus 1 to the second over n plus 1 factorial. That's the n plus first term divided by the nth term is 3 to the n times n to the second over n factorial. We don't need the absolute value symbol since everything is positive. So in the next step, we'll simplify the complex rational expression and write it as 3 to the n plus 1 times n plus 1 to the second over n plus 1 factorial times n factorial over 3 to the n times n to the second. We'll simplify this using properties of exponents and algebra and factorials. So we see we have 3 to the n plus first in the numerator as a factor, and 3 to the n as a factor in the denominator. So for now, let's replace 3 to the n plus 1 with 3 times 3 to the n. And the n plus 1 squared, I could just leave it the same, but I'm going to write it as n plus 1 times n plus 1. And then we have the n factorial. And in the denominator, the n plus 1 factorial, we'll write that as the factor n plus 1 times n factorial, and then times 3 to the n times n to the second. And we get some cancellations. 3 to the n divided by 3 to the n, those cancel. N factorial divided by n factorial. 1 factor of n plus 1 from the numerator and n plus 1 from the denominator. So we'll write down what we have left. In the numerator, we have 3 times n plus 1. And in the denominator, we have n to the second. And that's all. So what does this limit equal? We can rewrite this as the limit as n approaches infinity of 3n plus 3 over n to the second. So this limit is 0. And so since 0 is less than 1, the ratio test says that this series is convergent. Okay, the next example, the infinite series, the terms are n to the third over negative 3 to the n, as n ranges from 1 to infinity. So this is an alternating series. So let's see if we can apply the alternating series test. Check using the alternating series test. Okay, so the positive terms of the sequence in the series have to decrease. So we want to know if n plus 1 to the third over positive 3 to the n plus 1 is less than n to the third over 3 to the n. Well, what do you think? The denominator is exponential, and the numerator is polynomial. The base of the exponential is greater than 1. So this denominator is getting bigger or faster than the numerator. So this will eventually be true, even if it's not the case for 1. When n is 1, what do we have? We have 8 over 9 and 1/3. 8 over 9 is greater than 1/3. So it's not true when n equals 1, but it will be eventually. Another alternative is to look at the function f of x equals x to the third over 3 to the x, and find the first derivative and then determine where the first derivative is negative. So why don't we do that for a minute or two? The first derivative using the quotient rule, 3x squared times 3 to the x minus x to the third times the natural log of 3 times 3 to the x over the square of 3 to the x. So in the numerator, we can factor out x to the second times 3 to the x. And we'll be left with 3 minus x times the natural log of 3. And then the denominator is always positive. So this will be less than 0, which and on the interval where the first derivative is negative, the function is decreasing. So this derivative will be less than 0 when 3 minus x times the natural log of 3 is less than 0. And if we solve this for x, this will be true when x is greater than 3 divided by the natural log of 3. Okay, so the positive terms do decrease after a point, after a certain point. And then the second condition for the alternating series test, what's the limit of n to the third over 3 to the n? Well, we could use L'Hopital's rule repeatedly, since we start out with infinity over infinity. But we know that 3 to the n gets large pretty fast compared to n to the third. So this limit does equal 0. And so both of the conditions of the alternating series test are satisfied. So this means that the series converges. So to emphasize the alternating series test, the two conditions, one is that b sub n plus 1 is eventually less than or equal to b sub n. And then the second condition is that the limit of the sequence b sub n is 0. All right, the next example, the infinite series, the terms are n over n plus 1 to the n squared. N starts at 1. So any suggestions on which test to use to determine if this series converges or diverges? The outer exponent is n to the second, so maybe the root test, we can try the root test. The root test, the limit as n approaches infinity of the nth root of the absolute value of n over n plus 1 to the n squared. Once again, we don't need the absolute values because all of the terms are positive. But when we compute the nth root of n over n plus 1 to the n to the second, what does that simplify to? Well, I could just tell you, or maybe we can do it in a couple of steps. We don't need the absolute values, so I'll just write this as n over n plus 1 to the n to the second. And when we take the nth root of that, that's equivalent to raising it to the exponent 1 over n. And then we apply one of the properties of exponents. If we have something raised to an exponent, and if that entire expression is raised to an exponent, we can multiply those exponents. So n to the second times 1 over n is n to the second over n, or n. So this becomes the limit as n approaches infinity of n over n plus 1 to the n. And now all we have to do is compute that limit. Do you know what that limit is equal to? We'll do an algebraic maneuver here. And then after that, it might look more familiar. N over n plus 1 is equal to 1 over n plus 1 over n. So in the next step, we'll do a couple of things. When we apply the outer exponent n, 1 to the n is just 1. And so the exponent n applies to n plus 1 over n. But n plus 1 over n is n over n, or 1 plus 1 over n. So now we have this limit, the limit of 1 over the quantity 1 plus 1 over n to the n as n goes to infinity. So does anything about this look familiar now? So the numerator is 1. What's the denominator after we compute the limit? Yeah, it's the number e. We saw this recently. The limit of 1 plus 1 over n to the n is just e. And 1 over e is less than 1. So by the root test, since the limit of the nth root is less than 1, the series converges. The series converges. All right, let's look at the next page. Three more examples. In this series, the terms are n factorial to the n over n to the 4n, and n ranges from 1 to infinity. So it seems like the root test is a good candidate since the numerator is n factorial to the power n. In the denominator, n to the 4n is equivalent to n to the 4th to the n. So the root test looks like that might get us somewhere. So the limit as n approaches infinity with the nth root. Since everything is positive, I'll omit the absolute value symbols. So the nth root of n factorial to the n over n to the 4n. And then the nth root of n factorial to the n is n factorial in the numerator. And in the denominator, the nth root of n to the 4n is just n to the 4th. So it doesn't take too much convincing to show that n factorial grows a lot faster than n to the 4th. So this limit is infinite. Since infinity is greater than 1, this series diverges by the root test. Okay, the next one, the infinite series, the terms are tangent of 1 over n as n goes from 1 to infinity. Okay, I'll open it up for suggestions. I'll give you a few seconds to make a suggestion. I might not follow your suggestion, but what did you try or what would you try to test this series? I'm going to use the limit comparison. With the series, the harmonic series. So what do we know about the harmonic series? It diverges. And remember the limit comparison test? So I'll just write down the essentials of the limit comparison test. If the limit of a sub n over b sub n is equal to a positive number c, greater than 0. Well, c greater than 0 means it's positive and finite. Then the two series of the a sub n terms and b sub n terms are either both convergent or both divergent. Okay, so I chose a series that I know diverges. So if I compute the limit of the ratio of the terms from the two series and get a limit that is a positive number, then I'll know that this is also divergent. If I get something else, then we'll have to use a different test. Okay, so the limit as n approaches infinity of tangent of 1 over n divided by 1 over n. What next? Well, tangent of 1 over n is sine of 1 over n times cosine of 1 over n. And think of the 1 over n in the denominator as 1 over n over 1. So I can write this as 1 over n. And then we'll rearrange the terms in the quotients and write this as the limit as n approaches infinity of sine of 1 over n over 1 over n times 1 over cosine of 1 over n. And now we can compute the limit. Notice that as n approaches infinity, 1 over n approaches 0. So you may have seen in Calc 1 a famous limit. From Calculus 1. I'll use the variable x here. The limit as x approaches 0 of sine of x divided by x. Do you remember what that limit is equal to? It's equal to 1. So that's what we have here, because as n goes to infinity, 1 over n goes to 0. So the limit of sine of 1 over n as n goes to infinity is 1. And 1 over n goes to 0, and cosine of 0 is 1. So this limit is 1 times 1, or 1. Since 1 is a positive number, and we're using the limit comparison test, that means that both series diverge. Our series that we use to compare is the harmonic series. So that means the series that we're testing also diverges. Or is divergent. Okay, the next one. What should we do for the next one? The series, the terms in the series are 1 over n to the second plus 1 over 2 to the n, as n ranges from 1 to infinity. So with a little practice, you'll at a glance know exactly what's happening, what's going on here. Well, consider this series where the terms are 1 over n to the second as n goes from 1 to infinity. And then another series as n goes from 1 to infinity of 1 over 2 to the n. This series on the left where the terms are 1 over n to the second, what do we know about this one? Yeah, it's a p series. P is equal to 2, which is greater than 1. So that means it's convergent. And what's the other series? 1 over 2 to the n. What kind of series is that? So this could be written in a different yet equivalent way, starting at n equals 1 to infinity. We could write this as 1/2 times 1/2 to the n minus 1. So now does it look familiar? This is a geometric series, and the common ratio is 1/2. So it also converges. So geometric series, the common ratio is 1/2. For a geometric series converges if the common ratio is between -1 and 1. So this is convergent. And then in section 11.2, we have a theorem that says if two series are both convergent, then the sum of the series, or written as a single series of the sum, is also convergent. So if this is convergent, and we add it to another series that's convergent, then we can write it as a single series if we add the terms, and we'll still have a convergent series. So that's what we have here. So it's convergent. Okay, we can get started in section 11.8 on power series. Power series is a series of the following form. The terms in the series are c sub n times x to the n, as n ranges from 0 to infinity. And if you write the first few terms, it's c sub 0 plus c sub 1 times x plus c sub 2 times x to the second, and so on. It's called a power series because the individual terms in the series are power functions. So you might remember that definition. Power function. An example is f of x, well, x to a constant exponent. So a specific example, f of x equals x to the fifth, is a power function. So the individual terms are just power functions, hence the term power series. X is a variable, and then the coefficients are c sub 0, c sub 1, and so on. For each fixed value of x, the infinite series, c sub n times x to the n, is a series of constants that can be tested for convergence or divergence. And so a power series may converge for some values of x and diverge for other values of x. And the next sentence, the sum of the series is a function, f of x equals c sub 0 plus c sub 1 times x plus c sub 2 times x to the second, and so on. So it looks like the terms are from polynomial functions. It's just that a series has infinitely many terms. The domain is the set of all x for which the series converges. Okay, a special case of a power series is if all of the coefficients are equal to 1. If c sub n is equal to 1 for all n, then f of x is the infinite series 1 plus x squared plus x to the third, and so on. But in that case, the series is a geometric series which converges when the absolute value of x is less than 1, and it diverges when the absolute value of x is greater than or equal to 1. Okay, the more general form of a power series looks like this. The terms are c sub n times the binomial x minus a to the n. So if you expand it, it's c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared, and so on. This is referred to as a power series in the binomial x minus a. It can also be called a power series centered at a, or it might be called a power series about a. Okay, theorem 4. For a given power series, the terms are c sub n times x minus a to the n, as n goes from 0 to infinity, there are only three possibilities regarding the domain or the solutions. One possibility is that the series converges only when x equals a. A second possibility is that the series converges for all real numbers. And then a third possibility is that there is a positive number, capital R, such that the series converges if the absolute value of x minus a is less than R, and diverges if the absolute value of x minus a is greater than R. The case where the absolute value of x minus a is exactly equal to R, those have to be tested individually with each power series. Okay, in the next paragraph, the number capital R in case 3 is called the radius of convergence of the power series. And the interval of convergence of a power series is the interval that consists of all values of x for which the series converges. In case 1, when the only solution is x equals a, then the interval of convergence consists of a single point a. In case 2, the interval of convergence is from negative infinity to infinity. And then in case 3, there are 4 possibilities for the interval of convergence. It's either the open interval a minus r to a plus r, where the endpoints are excluded. A second possibility is half open, half closed, a minus r to a plus r, excluding a minus r, but including a plus r. The third possibility is half closed, half open, from a minus r to a plus r, including the endpoint a minus r, but excluding the endpoint a plus r, or the closed interval where both endpoints are included. So as I mentioned earlier, the endpoints have to be tested individually to determine if they are included or excluded from the interval of convergence. Okay, it's noted in the textbook that the ratio test is usually used to determine the radius of convergence, capital R. And then the endpoints of the interval of convergence must be tested by some other means, since the ratio test is inconclusive when the limit of the absolute value of the ratio is equal to 1. Okay, we can get started on some of the examples of power series. So find the radius of convergence and the interval of convergence. So we'll take the textbook's advice and use the ratio test to see if we can find the interval of convergence as well as the radius of convergence. Okay, so we start out with, in the ratio test, so we have the absolute value of -1 to the n plus 1 times n plus 1 times x to the n plus 1. divided by -1 to the n times n times x to the n. When we apply the absolute values, we can get rid of the -1 to the exponents. So we'll have n plus 1. Since x is a real number, then we'll put x inside the absolute values. So the absolute value of x to the n plus 1 over n times the absolute value of x to the n. We can simplify this further because the absolute value of x to the n plus 1 divided by the absolute value of x to the n will simplify to the absolute value of x in the numerator. So we'll write that in the next step. Okay, for each fixed value of x, notice that when we consider x as just some value, some real number, it's unaffected by what n does. And the limit of n plus 1 over n is 1, so this limit is equal to the absolute value of x. But since we're using the ratio test, how do we determine the x values that the series converges? So when we apply the ratio test and compute the limit, it converges when the limit is less than 1. So the absolute value of x is less than 1. And so the radius of convergence is 1. And then we'll find the interval of convergence. So we're going to solve this absolute value inequality. If the absolute value of x is less than 1, then that means -1 is less than x, which is less than 1. But the ratio test doesn't tell us whether the endpoints are included or not. So we have to consider the series for each of the endpoints. So let's start with x equals -1 in the infinite series. So we can probably do that down here. So we have -1 to the n times n, and then replace x with -1. So we have another -1 to the n. So -1 to the n times -1 to the n is +1 regardless of the value of n, right? So this is the series as n goes from 1 to infinity of n. So does this series converge or diverge? Well, this series is 1 plus 2 plus 3 plus 4 plus 5. So it diverges, right? So that means we exclude -1 from the interval of convergence. Check the other endpoint. Check x equals +1. So this time, when x is +1, 1 to the n is just 1. So we just have -1 to the n times n. So what about this series? Does this series converge or diverge? Think about what the partial sums do. So we start at -1, then we add 2, so we have a sum of 1. And then we add -3, we have a sum of -1. We add 4, we have a sum of 1. So the sequence of partial sums is going between -1 and 1 repeatedly. It's not converging to anything, it's diverging. Another way to do it is use the test for divergence. The limit, as n approaches infinity, -1 to the n times n does not exist, because for each positive integer n, the terms in the sequence go from 1 to -1, 1 to -1. So the limit does not exist. The series when x equals 1 diverges. And so the interval of convergence is the open interval from -1 to 1. That's the interval of convergence. Okay, that's all we have time for today. We'll do a few more of these problems tomorrow. So go ahead and sign in for attendance.